Well, welcome to the third and final class in the Advanced Lisp series. There are a couple of people who are going to join us in a second, but I'm just going to get started because we still have a lot of material to cover. Now, we're going to start out looking very quickly at the homework because the homework was a reasonably complex project to set up a scheduling system for an office. And we're just going to run through the code and just so you can see it, but it's, I'm afraid, somewhat too complicated to go in detail. You start out by, you're going to do a calendar, so you have to represent various things like months. And here we're defining symbols, global symbols, with the names of the 12 months. And so we have the name of the month surrounded by stars, indicating it's a global symbol, and then the number of the month is the value of the variables we're creating. These are constants because we're never going to change them. January is going to be the first month as long as you run the application. And here we have a class called datetime, and it's got slots, year, month, day, hour, minutes. And here we have the constructor function makeDate, which takes an argument for each slot and creates an instance of a datetime object. And here's an example. When you have a datetime instance, you want to print it out in some way that's desirable, and so we have a couple of examples here. They're both of them using, well, this one's using format and this one's using print, and you try those out and you get a printed representation of the date. When you have two date instances, you want to see whether they're the same. So they're the same if they're the same year, month, day, hour, minute. And also you have two date objects. One can be less than the other if it occurs earlier, and these calculations here figure out whether the first date is less than the second. And some more machinery for comparing dates. I'm just running through these things quickly because, as I say, we don't really have time to go into them in detail. One problem when you're working with dates is a year a leap year, because that means there are 366 days in the year, and you have to account for February 29th. And here's the rule: is leap year is every year divisible by 4, except the years divisible by 100, except the years divisible by 400, which is why the year 2000 wasn't a leap year. And here's a method for copying a date object, creating a new date object from an existing one. And so here we add a number of, we create a new datetime object with a number of minutes later than the current one. And now we start out, what we're doing is an appointment calendar, and we start out creating classes of appointments. And one kind of appointment's a patient appointment, and there's a meeting appointment. And we start creating schedules, and we also start looking for conflicts. And the type gets really tiny on this slide, I'm sorry. But here we have a patient appointment, and what do we got? 2 patient appointments, and we see whether they conflict or not. And now we start building schedules. And we also have a way of rescheduling an appointment. and now we start making patient appointments for a patient. We give them a list of appointments, doctor appointments for doctors. And whenever you have a database, this is just some information. So what this schedule and appointment thing is it's basically a database. And if you go into an actual doctor's office, most of the time it is kept on a big book, which has been designed, 100 or 200 years ago by stationery companies to assist doctors. And the way they know where there's a conflict is they open the book and they see where anything's written in a particular time. But we're doing this online, and so we are storing data online. And so the question is, how should this data be stored? And one is you can just have an ASCII file with the data, and you have, in that case, you must have some kind of delimiter, and you typically use the tab character or commas as delimiters. So when you read the file in, you find the tab characters or the commas, and that's how you know you've finished reading one kind of object. In that case, you would print Lisp, or you could print Lisp code to a file, which, when loaded, would recreate the schedule. So you would be printing a lot of, create date or make date time forms and things to set up the schedule and so on, almost exactly the forms that you typed in when you had set up your application and created them online. There is a FASL read and a FASL write, where in Allegro CL specific, it's not standard Common Lisp, where you can generate binary files. In my view, this is not really the way to go because these have specific uses and they're a little bit quirky, and they're not actually very happy with CLOS instances, but they do exist. You can have an outside database, Microsoft Access, Oracle, various SQL databases, another one called MySQL. Many of these Allegro CL provides interfaces to. You can save your entire Lisp image. And I should point out that in Allegro CL 8.0, there is a new within Lisp database called Allegro Cache, which serves similar purpose to many of these standard databases. So those are all just various ways that you might store the data, and which one you use depends on your needs and the particular problems you're dealing with. The advantage of a comma or tab delimited ASCII file or of a is that presumably it can be interpreted. If you have a copy of it somewhere, with a little bit of work, you can reconstruct the information. Similarly with the Lisp code, although you have to reconstruct the information, it's harder to do unless you actually have the application running. The rest of these are all binary files, which means that if you've lost the tools for reading them, they're probably uninterpretable. So that's all I want to say about the homework. And we left off last time in day 2, and we're just going to finish up on CLOS, and then we're going to go through day 3, some of which, day 3, we're going to talk about some performance considerations with CLOS, and then certain features like garbage collection and error handling, and end up with a discussion, not too deep, but of the Windows integrated development environment, where you can build the graphical user interface to an application using interactive tools that are provided. And we might be able to do a couple of quick examples with that. So remember that we have various kinds of methods. We have what are called primary methods. We then have before methods and after methods. Before methods, if they exist, run before the primary method runs, and they go least specific first to most specific. The after methods go most specific to least. The around methods, an around method actually surrounds everything, and no other methods will run unless the around method makes a call to the call next method operator. And when an around method calls call next method, it will go to the next least specific around method and run it, or if there are no more around methods, it will go off into the before methods if there are any, and the primary methods, the most specific primary method. If you have a call next method within a primary method, it will go to the next most specific primary method. And call next method can be called with arguments. If it isn't called with arguments, it's called with the same arguments, actually unmodified, as the original method was called with. So here we are calling it with a specific stream as an argument rather than the stream that was passed in. Here's a call next method example where we're this is the actual slide we left off on last time, where we start out with a method which is specialized on the first argument when it's a list, and another method specialized on the second argument when it's a number. And in both cases, we check to see if there is a next method, and if there is, we call it. So when we call with a list and something that isn't a number, there's only one method runs, the one where it's specialized on the first argument. Where we call with a non-list and then a number, the second method runs. But where we call with the first argument a list and the second argument a number, both methods are run. The one that's run first is the one that's specialized on the first argument in the list. There is a way, as we will just mention briefly later, to tell the methods to run in a different order, say starting with the one that specializes on the second argument, if there is one, and then going to the first argument. But by default, you always go to the method specialized on the first argument if the argument values are, there are methods for each argument value. Setf methods are a way of defining a setf operator which will set the value of a place. Typically, in this case, we are having a setf method for setting a slot of a particular class, in this case the class of squares. So part is an example of a square. Whenever you create an instance of something by calling the function makeInstance, a generic function called initialize-instance, a system generic function called initialize-instance is called, and it does the actual work of creating the instance. And you are allowed to write, well, you typically write after methods on initialize-instance. You can also write before methods. You should absolutely never overwrite the primary method, or the entire system will come to an unpleasant end. Because generally you won't have it doing the things that internally we know are supposed to be done, probably even if you have the source code. But you're free to write after methods, and typically what you do with an after method is you check to see that things were reasonable, or you push the new instance on some list of instances created, etc., etc. So here we're defining an after method of initialize-instance when the it just takes one argument, one required argument, and as many keyword arguments as you like. And here we're specializing on the class square, and we are actually making sure that the width is greater than 0. Greater than equal to 0. If it's a negative width, we actually signal an error in this case. You want to have, typically you want to have a way to print out an object so that it provides the information that you are interested in. So you're allowed to define print object methods, and they take, a print object method takes 2 arguments. The first argument is the one you typically specialize on. The second argument is a stream where you're going to print things to, and that allows you to print things in a way that is useful to you. So here is we're creating an instance of a point, and here is what the standard way that Common Lisp prints out a point object, because that's what's returned. And here is, you call print C on the point, and it's now going to use the print object method you've defined. And so if you hadn't defined a print object method, it would look much the same as what's printed there. There are a couple of functions you should, operators you should know about. One of them is called print unreadable object, and there are many objects within Lisp. There are many objects that when you print them out, you can read them back. Numbers are an example of that. Simple vectors, even arrays, can be printed out, and as long as all of their contents are printed, if you're talking about arrays or vectors, when you read them back, you will have an equivalent object. But there are a number of things, such as function objects, some more complicated things, where it is not reasonable to print out in the, when you print something, all the information that is needed in order to recreate the object when it is read back in. And in that case, Lisp uses a notation which starts with a number sign or hash sign and then less than, and that tells the reader that, okay, I can't actually read this. And so if you try to read this back in, you'll get an error where it will tell you, I'm sorry, I can't read that object in. And so when you call print unreadable object, it will print things in that format, and it allows you to print the information between the less than and the greater than that you are interested in having displayed. Also, there's a global variable called print escape, and it's set by the pretty printer to indicate the desire for using this particular notation rather than just saying 0.32 or something like that. So when you are printing things out, there are various techniques you can use to have what's printed out be what you want. But you have to always remember that certain kinds of objects just can't have a printed representation that can reasonably be read back by Lisp. However, if you're looking at 0.32, you could read that in and parse it yourself, where you would read it in and you'd say, okay, point, that must be the class point, so I'll create an instance of that, and 3 and 2 are the values of the slots, and then you go on from there. You've got a class. It inherits from a whole bunch of superclasses. It may only have one direct superclass, or it can have 2, or as many direct superclasses, that is, one level up, as you want. And so the question is, how do things, you now have methods on perhaps many of those direct superclasses, and the question is, when you therefore run the generic function on an instance of your class, you have no method specialized to your class. Which of the methods specialized on the direct superclasses is going to run? And it uses what's called the class precedence list to determine the methods that run. And we've talked about the class precedence list before. Even though things may have multiple direct superclasses, They are ordered according to the class precedence list, and that's typically the order in which they were listed in the second argument to def class, which is the one that lists the direct superclasses. So if you ordered my class 1 first and my class 2 second, then the my class 1 has precedence over my class 2. Always the most specific applicable primary method runs. All before methods run the most specific first. All after methods run the most specific last. I think I said that backwards earlier, but the before methods, it always takes the most specific and then goes to the next most specific all the way out to the least most specific. The after methods run in the opposite order. Around methods, again, always the most specific runs, and then so on when there's a call to call next method. So here is, we've got def class basic part, and it has no listed superclasses, so it's superclasses standard object. We've got def class rectangle, whose superclass is basic part. A class always has precedence over its superclass. So if there's a method on rectangle and a method on basic part, the method on rectangle will be the primary method that will run. Rectangle has precedence over basic part. Basic part has precedence over standard object. Standard object didn't appear there, but when you're defining classes, standard object is always a superclass if none other is listed. Standard object has precedence over T. T is the superclass of all the classes. It's way at the top of the tree. And the precedent list that satisfies all these constituents, so here's the precedence list for rectangle, is rectangle, basic part, standard object, T. So, of course, when there's more than one direct superclass, things become a little bit more complicated. So here is a modified, let's see, this is a new rule. Here is a rule, second rule. Each class definition sets the precedent order of its direct superclasses, as I said, and classes appear only once in the class precedence list. So here we have rectangle, and its superclasses are, I think at least some of these, let's see, basic part was defined before. Let's assume these are also defined. And its direct superclasses are these three classes: selectable part, savable part, basic part. And then it has slots X, Y, width, and height. Selectable part is first in this list, and therefore it has precedence over savable part, which has precedence over basic part. So it's the order that the direct superclasses are listed in the def class form. So I'm sorry about the slightly small type, but I want to show one example of this. Here we have a class bar and a class baz. Neither of which, they just are both standard objects. And we have a method on foo, a method foo defined on bars, on instances of class bar. That simply prints out I am bar. And we have one on instances of class baz that prints out baz I am. So now we have B sub 1 has bar as the first superclass, direct superclass, and baz as the second. B sub 2 has them in the other order. So we get an instance of each, B1 of B sub 1, B2 of B sub 2. Now we call foo on B1. It says I am bar because bar was, there are methods on both bar and baz. Both are direct superclasses, but bar is the one that appears first in the list. We do the same thing on a instance of B sub 2, and we get baz I am because baz appears first in the list. So there's sort of a lot of lines here, but this is this is kind of the example from which all other examples can be built. And if you understand this page, you'll understand the use of the class precedence list as regards direct superclasses. So when you're writing a class program, specify the problem, identify the objects of interest, then you design the class hierarchy. Then you design the client interface, then you get it to work, and usually then you have to extend it. So here are some good advice when you are writing applications. You don't want the users of your application, typically you don't want the users of your application to know about the internal structures. Because if they do, they will start writing code, assuming that they're writing code to extend the application, which uses the nature of those internal structures. And if you go around and change them later, their code's going to break. You typically provide specialized methods on describe object and print object, and you offer accessor methods in the API. You don't tell people the names of slots or tell them to use slot value. You provide a constructor function like we've done make point, and don't tell them to call make instance or tell them how to call make instance. And you specify your generic functions, and you tell people how it's done, so you tell the client can then write their own methods. And you're allowed to tell them, that is the client, that is your user, and you're allowed to tell them things like we do with initialize-instance, which is that they should only write before methods or after methods and not replace the primary method if that is a reasonable thing to say. Or you can tell them that if they specialize on one of the classes, so they have their own subclass, and they write a primary method for that subclass, it must call callNext method so that your primary method on the superclass will also run. Just some words on class hierarchies. Superclasses inherit structure via slots. Subclasses inherit behavior via method. Subclasses inherit structure and behavior. Multiple inheritance supports modular reuse without copying. So if you have a class called label object, and then you can mix it in with, labeled this and labeled that, labeled circle, labeled rectangle. Labeled object is going to have a slot, which is one of them is the label name, and it may have a print method that's suitable for using print object method that's suitable that includes the label name, etc. And your labeled circle, if you specify that as a direct superclass and labeled rectangle, will inherit all that behavior without you having to reconstruct it. Often in your class hierarchy, you have abstract classes that you don't intend to instantiate. Labeled object, just guessing, I don't think we defined the class, but that's typically a class which is one which is providing some behavior, but you don't know it's providing behavior for any kind of object and therefore has no specific behavior of its own. It is only providing behavior for things that are specific kinds of objects like circles and rectangles. Often these abstract classes are have the word mixin, M-I-X-I-N, at the end of their name. And when you see a class that's labeled something hyphen M-I-X-I-N, you can be certain, almost certain, at least by convention, that you're not supposed to instantiate that class. You're supposed to use it as a superclass for other classes that can be instantiated. So now we're just going to run through, not too many more slides on today, and I'm going to run through, some of this is repeating what we've already done. But the first thing is we've defined generic functions, and we haven't mostly been calling def generic, which simply defines a template for methods. We've mostly been calling def method, and when you call def method, if there isn't already a generic function defined with a particular name, it will create a call to def generic and define the template based on how you define the method. But you can call def generic, and there are sometimes reasons for doing that. Now, when you are providing methods on different classes, and you're providing, different foo methods on different classes, there are some rules about the argument lists. All the methods must have what are called congruent argument lists. Now, the argument lists are congruent when they have the same number of required arguments. That's very important. When you have the same number of optional arguments and rest and key arguments are compatible. And we'll see what that means in a minute. If you can avoid optional arguments, it's generally a good thing, and never should have more than one, in my opinion, on generic functions, because it is gets just more and more complicated. Now, if you try to define a method with an argument list that isn't congruent to existing methods or the def generic call, you'll get an error. So, doesn't matter what the argument names are. X and Y, both required arguments, height and width, absolutely congruent. The only important thing is 2 required arguments and no additional arguments, 2 required arguments and no additional arguments. N and optional int is not congruent with this number and 2 required arguments. 1 required and 1 optional is not congruent with 2 required. And occasionally this is actually kind of annoying, but that is one of the rules. Now, what we meant by rest arguments and key arguments, here we have 1 required argument and then any number of arguments you like. That's what a rest argument says. And here you have 1 required argument and 3 keyword arguments. And these are both congruent. And even though you might call this one with more arguments or without specifying keywords, that would not make sense for this one, that's an error that will be handled at runtime. It is not an error to define these 2 things. Typically, you're doing this because you're just specializing on the first argument, and you really don't care what the keyword arguments are. While in this case, you need to know the keyword arguments are presumably providing slot values or something, and you need to know what these values are. Usually when you have an and rest argument, it means you're going to ignore it. And it's just there in order to provide for congruence. By the way, if when you are writing generic functions or when you are writing methods, you have to specify a whole bunch of arguments, and often you don't care about some of them. For example, you have 2 arguments, height and width, and you're only interested in printing out the height. You don't care, it's just some method for printing out the height, and you don't care what the width is. Then when you compile things, you'll often get a message saying, well, you had this argument width, and you didn't use it. Are you sure that wasn't a mistake? And there's a declaration called the ignore or the ignorable declaration, where you can tell the compiler, I'm not going to care about that argument, and don't be surprised. And typically when you're writing your own functions, you don't ignore your arguments because what do you have them there if you're going to ignore them? But when you are writing generic functions or methods, you're required to specify all the arguments in order to get a congruent argument list, and therefore you often may be ignoring arguments. If you're specializing on any argument, that counts as not ignoring it. So here's some more keyword congruencies. You can't have no keyword arguments in one method and keyword arguments in another. You can have there's a lambda list keyword called allow other keys that comes after and key, and that tells you tells the system specify any keyword arguments you want, and presumably the body of the code will do something with them. And that's kind of like an and rest argument, except it has to be in keyword value pairs. But that is congruent because the one that's most specific, you just want to know that the ones that are more general will allow for the most specific one. and this one certainly will allow for any number of keyword arguments, as will this one where you have the same keyword argument, the same first one, and then you have an and rest argument that says, okay, and then any other additional arguments you want. When you have and key and rest, the keyword argument has to be specified first. So now let's look at specialization of slots. Here we have a class of labeled rectangle with the superclass rectangle. It's got a slot label with an int::label. It's got a slot font with some initial value and an accessor rectangle font. And now we have a Roman rectangle, which is a subclass of this. And it has also, you're specifying a font slot here, and it has a different default font value. So Roman rectangle inherits from labeled rectangle, so the font slot already exists. Here you are specifying it differently, and your more specific specification will be used when you're creating instances or working with instances of Roman rectangle. So once again, here's the allocation class. When you're creating a shared slot, you can use them as an alternative to global variable, but and the shared slots are stored within the class, not the object. And when you change the value in one instance, the change is visible in all instances. In the earlier, we saw how you could just write a method, and that's often just as easy a way as having a shared slot. Basically, you're not going to use shared slots probably, so I'm going to go through this very quickly, but they are inherited, and you can shadow a slot value of a superclass by defining it as a direct rather than a shared slot. And then instances of the subclass will see different values, and changing the value won't affect the other instances. So subclass can change the slot allocation by specifying instance allocation instance rather than allocation class. And now, you can call def generic. You don't have to. When you create a function you call fun, you have to. But you don't have to call def generic, and def generic has no body, doesn't do anything. It only defines a template. Typically, you call def generic in order to have declarations that apply to the whole generic function. And typically, you just get an optimized declaration that says you want the compiler to compile either as fast code as it can or as safe code as it can or whatever. But here's the one. Then you also have documentation, where you can define a documentation string for the generic function, and a bunch of things we're not going to describe in detail having to do with the generic function class and the method class and certain method combination. We may go into method combination. But the one that's important that you may want to use is argument-precedence-order. And remember, I had this example before where the first argument was specialized as a list, and the second argument was specialized as a number, and then we called it with a list and a number, and the question, it ran argument 1 as a list. We don't have any call next method here, so it just runs one method. Now, we redefine the generic function template by saying the argument precedence order is B first, then A. That's all we do. We don't redefine any of the methods. Now when we call it with a list and a number, it runs the method for the second argument being a number as the primary method, not the method for the first argument being a list, because we dynamically change the argument precedence order. And remember, that means that the argument precedence order is determined at runtime. It isn't determined beforehand, because here we've changed it, and the behavior changes right away. You can call def generic. If you just define the generic function template with def generic, you haven't defined any methods. Calling a def generic again just simply redefines it. So you can make any changes you like. You can always change the argument precedence order, even if there are methods. You can change the documentation. You may or may not care. You can change the default method class, which we're not going to go into, but you cannot change the lambda list except for the same lambda list with the same congruence rules, and what would be the point? You can't change the method combination, and you cannot change the generic function class. You can redefine a method with the same specializers and qualifiers. It overwrites the old one. The specifier and qualifiers change, then you're defining a new method. You can remove methods with the function remove method, and there's also an Emacs command for it. Now, when you have a class, when you have an object, you can find the class of the object. I'm sorry, when you have a class name, you can find the class object associated with it by the function find class, and it also works for built-in Common Lisp types, most of which are classes. Class name takes a string which names a class, and takes a class object and returns its class name, and so its value is a string. When you have an object, you can get the class of the object with the class of function, and it gives you the most specific type of most specific class of the object, and class of many built-in types, like a string, give you something that looks like this. This is, when you see built-in class, it's one that's defined by the Common Lisp spec or Allegro Common Lisp itself. Generally, when you see built-in classes, you're not allowed to call make instance on them. Not always, but there are very few examples. If you want to create a string, you've got to call make string or use one of the reader macros like the double quote to create strings. You can't call make instance of built-in class string. Almost all built types have corresponding classes, so string as we saw, but some of them don't. There's no class named bit, and there are various other things that describe actually really tiny typical objects. Typically don't have classes because that would clog everything up. You can, so we just see here, we're just showing the cons as a class and symbol as a class. And rectangle is not a built-in class, it's one that we've already defined. And so here are some of the class hierarchy here. The T at the top, symbol, what do we got? Sequence, array. Sequence is a list and a vector. Vector is also a subclass of array. There are bit vectors. Lists can have conses. Nil is a subtype of list, and it's also a subtype of symbol, etc. You can, there are tools within the integrated development environment on Windows where you can look at superclasses and subclasses, and you can also build class tables much like this, except they typically put the top at the left and build to the right because that works better. Now, defstruct, as we mentioned that before, as kind of a simplified way of defining of def class. A structure is a simplified example of a class, but defstruct also defines classes. So when here we're defining an S rectangle, a structure rectangle with slots XY with height, similar to how we would have done it with def class, except the in def class, all the slot names appear in a list. In def struct, you just kind of go off and start listing them, but they're not bundled up in a list. Just a small difference in the way the definitions are done. When you create an example, when you create a def struct, you get an automatic constructor function, and it is an instance of structure class, S rectangle. That's structure class means that this is a class created by defstruct. And you can define methods on that. but the accessors are not generic functions. The accessor to the rectangle, S-rectangle width, is an ordinary list function. It is not a generic function. You cannot define your own methods on it. You cannot define an around method on it, for example. Okay, now just a few more slides on class elements of style, then we'll get to the slides for today. Don't use type P. So is X a rectangle? Define a function called rectangle P. And here's how you would do it. Def method rectangle P for any object returns nil, except if the object is a rectangle, returns P. Again, don't reveal to your users the internal structure of your classes, because that makes it difficult for you to change. Don't use slot values, same reason. Use create or use accessor functions. This one's I don't have an example of this, but if you find that you've defined a slot and you're spending a lot of time looking at the value in the slot, trying to figure out what it is, and then changing your behavior depending on what the value of the slot is, probably you need more slots. Constructors. Don't get your users to call make instance. Make a constructor function typically called make and then the class name. And again, hide your data structure decisions. Makes it easy to change. Yeah, I should have print object methods. Good idea. It is often useful to define EQL methods with symbols. And as it says, that's like a case statement, but more modular, more easily extended. And so here we're defining a whole bunch of methods on different, when the first argument is the symbol, redraw, you do something when it's the symbol, iconify. When it's a symbol which we don't have a method for, you'll get an error, much as eCase would give you an error. Or you could define it on P, and just say, you know, get it to do something, whatever it is you want it to do, and then it will, you know, usually nothing. And then it will only do something specific in these specific cases. And the thing is that, you know, if you had to rewrite your case statement, you'd have to go find the code, find the case statement, rewrite it, and then, you know, reload or recompile the code. But if you wanted to find additional methods for handle event on different symbols, well, you just call def method and you're done. The drawback is the method dispatch is a bit slower. So if these things are in tight loops called many, many times, you might worry about that. A guy named Peter Norvig, famous Lisp programmer, you know, he likes to use set2 rather than setf. Actually, we prefer the other way. Use second, he prefers to CADR, be concise, don't reinvent tools, etc. This is what you do when you're doing CLOS programming. And that's the end of the slides. So we're going to move right on to the slides for today, day 3. And so we've been going through this. Obviously, methods allow you to customize your behavior. You define primary methods, also before, after, and around methods. All before methods run first, most specific first. All after methods run after, most specific last. The most specific primary method runs. Call next method will run the next most specific primary method. We had examples of that. All after methods run, etc. Around methods wrap around all other methods. The most specific around method runs. And then additional around methods or before primary after methods run only if call next method is used. Around methods allow inserting logic that will determine whether methods run at all. I don't usually just read the slides, but in fact these slides are exactly what you want to say. So that is the basic story of around methods. And you know, the thing about methods is that by using the different kinds of methods, by supplying more specific and less specific primary methods before methods, after methods, and if necessary around methods, using call next method when it's necessary, and if you are unsure if there's a next method, using next method P to test for it, because if you do a call next method and there is no next method, you'll get an error. It allows you to program at a very fine level and to modify things relatively easily and to do quite complicated things in a fairly simple or simpler and structured way. Methods, you can always redefine them at any time, even while an application is running. That's the feature of Lisp. You can define new methods at any time. If you call fmacunbound on foo, it destroys just as it would destroy in other words, remove the function definition that appears in the symbol function slot of the symbol foo. It destroys all methods and the generic function. And so sometimes you've defined methods and you've discovered, oh, I don't like that argument list because, I want a different argument list. It used to have 2 required arguments. I need 3 required arguments. You can't define a method with 3 required arguments when there are already methods with 2. So you just clear everything out and just start again. And sometimes that's what you need to do. Now, an interesting thing is that you can change the class of an instance of an object at any time. So here we have class C1, it's got slot X, Y, and Z. Class C2 has got slot A, Y, and C. Different init forms. Different slots, but the one slot they have in common, class C1 has the init form that is the default value 55, and class C2 has default value slot Y, the string. So we create instances class C1, and it inherited all the default values, X, Y, and Z is 10, 55, and 99. Now, we call change class, and we apply it to this thing we just created, which was of class, an instance of class C1, and we say, okay, change its class to class C2, and then you can give slot values using init args in the usual way. The init arg of the A slot is :A, and we're giving it the value 777. Now, what are the slot values? Okay, the A got slot value 777. The C slot down here got we haven't specified C anywhere, and so it got its slot value, default slot value, slot C, the string slot C. What about Y? Well, this object already had a slot called Y, and that slot already had a value, which is 55. That value is not affected. We didn't specify. We could have put a :Y here, and that would have overwritten it, but we didn't, so it inherited the slot with the same name when it changed from one class to another. So when would you use things like change class? You have an employee list, and you've got a class of person, which is just anybody. It could be an employee, it could be a consultant, it could be a customer, and you've got an employee named Joe Smith. And Joe Smith says, well, I want to spend more time with my family, but I'll continue consulting. And so you want Joe Smith to change from being a member of the subclass of person employee to being a member of the subclass consultant. And so you got the instance of Joe Smith, and you changed the class to consultant. Now, things like his name, his age, the aspects of his history, his address, his phone number, his whatever, all stay the same. Those slots are probably shared between employee and consultant. But supervisor probably applies only to employee, and the consultant has some other kind of name, and et cetera, et cetera. But that is an example where in a real programming situation you would want to change the class because the object actually has changed its nature in some way. Now, we're going to go through a number of slides that are going to just talk about performance considerations. Now, performance considerations are sort of a funny thing because computers are really, really fast now, and you want to know what the performance considerations are for. The typical things that you're interested in when you have an application is you want the time it takes to run the application not to be noticeable to your users. Now, that always can't be done, but that's your desire. If there's any interactive form of your application, if it's running so that it's not noticeable to your user, in other words, they put in some information and then you update it based on that information, and if they see that from a human point of view instantaneously, which is, like 100th of a second or something like that, doubling the speed of that application probably isn't going to do much good because, it may reduce machine resources, but it's not going to make your users think that you're tremendously clever. If you're doing some kind of calculation where you're interacting with other machines, then going faster and faster is often a good idea. But anyway, you have to think about performance considerations, and you want to think about them when they're actually affecting your life. So just some discussion about using generic functions rather than regular functions, using standard class, which is the one that you create with def class, structure class, which is the one that you create with def struct, and built-in class, which is one that comes already available with the system. You have to be sure you're looking at what your program requires, what, are there built-in classes that will do what you're looking to do, and if we do it in different ways, how much does it cost? Typically, you measure performance by defining a function that calls a macro called time, and then you call whatever it is you're interested in seeing how quickly it performs. In this case, how long does it take to create an instance of point, and you do this some number of times. Now, you want a number of iterations such that the loop takes at least a second, and then you calculate the number of iterations per second. And let me tell you, I can absolutely guarantee you that this thing has way too few, because this will take a microsecond or something. Typically, actually, you define the function with the number of iterations as the argument. So then you can start jacking that up until you get the speed that you want. Always compile things. The interpreter, which would run if you did not compile the function try, the interpreter is actually pretty slow because it's not designed to be fast. It's compiled code which is designed to be fast. So timing the interpreter for the most part is not interesting. The compiler also does all sorts of optimizations. That's why you always compile code. And obviously, this is sort of a bullet that's kind of, duh. You shouldn't create an instance if you don't have to, because it uses resources. And that's the whole point of going faster, is not to waste resources. You create instances with a call to make instance. You get multiple inheritance. You get all this stuff. You create instances of structures with a call to the constructor function that you created with the structure, but all instances of structures are actually vectors. So you're just creating a vector. An instance of a class is not a simple thing like a vector. It's a much more complicated kind of object because it will do a lot more stuff. But if you have a fairly simple data structure, often, and one that will be used a great deal, you might want to consider using structures created with def struct, because even though they're somewhat older technology, they're also simpler and, for certain things, faster. So here we have nice tiny type. But what we're doing is we're creating a structure called ship1, and we're creating a class called ship2. So when you create an instance of ship1, you know, how many bytes does it use? And the answer is typically, and these are on 32-bit lists, it's a little bit different on 64-bit lists, but it uses 24 bytes per instance as opposed to 48 bytes per instance of the class. And you would time a creation of here we have the try function where you do pass the number of times as an argument. And when you've compiled things, you get about 200,000 creations of the structure object per second, and actually roughly the same number of the class object, about 200,000 per second, except you pay a price on the first one. Now that price more or less disappears, but the first time it creates an instance of a class, it does a fair amount of work because a lot of the things associated with classes in Lisp are called lazy, in the sense that they don't do a lot of the work associated with creating a class object until you actually create the first instance, because why bother? If you're never going to create an instance of a class, then you don't have to, you can save doing that work. So whenever you have a class, the very first instance takes longer than any other, the creation, but not hugely significant when you're doing a large number. Let's see, did I read that right? Yeah, that's about the same. When you do an unoptimized make instance, and then you lose speed by a factor of 10. What makes this unoptimized? The compiler comes in here, and it says, class name is an argument. So I don't know how to create an optimized version of this call of make instance because I don't actually know what kind of class, what class they are going to supply. The optimized make instance, here we said make instance of ship2. And the compiler said to itself, to the extent that compilers are real people, well, I know everything about the class ship2. It's got an X slot, it's got a Y slot, and so if you're telling me to make a ship2, I know how to do it really fast because I don't have to go off and search the information and figure out what to do. But here, it doesn't know it's creating a ship2 until it actually at runtime. So the compiler can't use any of the available optimizations because the available optimizations are different for different classes. So that's why this is an unoptimized call, and the cost to you is about a factor of 10, from 200,000 to 20,000. And by the way, if you go and try these on your machine, it's quite likely, perhaps even certain, that you're going to get much faster results because we made these slides 4 or 5 years ago, and the thing about computers is that they get faster and faster. But it's likely that the ratios that we're talking about, the fact that creating a single structure and creating a single instance of a class using an optimized version of make instance takes about the same amount of time, and that an unoptimized use of make instance is about 10 times slower, it's likely that those ratios will still hold approximately. So if you have a function which is going to create an instance of different classes which has to be determined at runtime, and you know any of these classes, then you should use a cond form or a case form or something like that that will allow you to have as many specific calls to make instance with the class name provided as you can. And maybe you drop down at the bottom and you just have a non-specific call to make instance. But that's one way to optimize code when you are having to decide at runtime what the actual class you're going to create is. Now, another aspect of performance is slot value. Slot value, the function itself, can be as fast as 2 arefs, that is 2 accesses to vectors or arrays. The first looks up the position of the value in the instance vector, and the second actually accesses it. Now, when I said that structure instances are vectors and class instances aren't, the thing is the class instances are actually made up of a bunch of vectors, and one of them tells you what the names of the slots are and where you can go in the data vector to find the value of that slot. But a structure instance is purely a vector, and if you just looked at it, if you looked at one, it would, and said vector P, which says, is this object a vector? The answer would be yes. The slot reader, writer, and accessor that are provided that you've defined that we recommend that you use are nearly as fast as slot value. If you're looking at slot value versus structure accessors, the standard class, you get a whole bunch of stuff, while structure accessor doesn't, get all this stuff. You can't do change class. There are various kinds of error checking you can't do, et cetera, et cetera, et cetera. But destruct accessors are really fast as a result. Generally, the rule is the more you can do, the slower you are. Slot value optimize, you can optimize it, and but you can't completely inline it. You're generally having 2 memory references as opposed to 1. And if it's completely unoptimized, it is noticeably slow. And so here we have a comparison, and you get 2.2 million struct accesses per second and only 700,000, saying that the slot value access is probably 1/3 as fast as a access to a slot of a structure. Does this matter? Well, how many instances do you have? How many times are you accessing them? That's the question. If you're doing things in the millions, yes, it's beginning to matter. If you're doing, something just a few times, not a big deal. Slot accessors are generic functions, and this is said before, destruct accessors can be compiled in line or often faster. Just something to remember, because destruct accessors are compiled in line, you must recompile things if they change the structure. The structure is redefined. That's typically not necessary, recompiling all your code when you modify generic functions. So here we have, what do we got? We got a class called Buick. It's got a color slot, and here we're accessing the color slot of, let's see, we're creating, we created a Buick, and we accessing the color slot n times. Now, here is, that's just something you can try at home. Here is a function and a generic function call. The function, we take an argument, and we look at its type, and it's either a simple lock or it's a null lock, et cetera, et cetera. When we do this with generic functions, we just define methods for each one of these classes. And so you can always, as we said at the very beginning when we discussed generic functions, you can always implement the behavior of a generic function using cons and case statements and so on. You cannot, but the difference is that you want to add additional possibilities. You've got to redefine the function. You can just do this immediately with methods, and you can add additional methods at will. The call to seize the first call to the method is going to take longer than the call to the function, assuming everything's compiled here. Subsequent calls should be approximately the same, because they're roughly doing the same thing. They've got to do the same thing. They've got to look at the argument and figure out what it is. And you're either doing that in the function or outside of the function, but you've got to do it. And so let's see. We've got a function invert, and we're calling invert a whole bunch of times. And we got a function method nada, which does the same thing. And so we get about 3.5 million calls in both cases. Remember to compile everything here. We've got 2 arguments for specializing. I'm sorry, here on this method, we're not specializing on the argument, notice. But when we start specializing on the argument, we lose about 1/2 the speed. You could, you could represent objects using sequences with symbols for type codes, see. So here we have list P, list block, and if it's a list, we look at the car, and then if the car is simple lock, and so on and so forth. And this is a this is how would you represent an object? You can represent as a list with the first element of the list being the name of the kind of object, kind of the class name. And all this is saying is that's pretty inefficient. The advantage of doing it is that you can kind of build things up quickly, but you won't want to do it where performance is important. And typically you only do things like that when you're sort of starting out with your program and you're trying to get things working. You would then go and define classes and so on. Now, when you have a function and it has keyword and optional arguments, things slow down because it doesn't matter whether it's a regular function, generic function, it's got to parse the argument list. So the functions which are really critical to your application are called a very large number of times. Don't use keyword or optional arguments. You just, it says here that removing keyword processing increases performance by about a factor of 6. So we're talking a significant difference. Method dispatch is usually slow the first time unless there's only one method, but it speeds up because the system notices that you're calling methods that is the first time for any particular class and any particular specialization. But it notices that you're calling something specialized in a particular way, and it stores the methods in an efficient fashion. So the first calls to things are generally slow. That's usually not a big problem because usually we're talking about things that run pretty fast, maybe in a second as opposed to 1/100th of a second. So you get a big speed up from the first time, but unless it's a particularly, the dispatch portion of it isn't going to contribute a huge amount, is the point there. If the function takes a long time, it's because the body of the function is doing a lot, and that body gets executed after the dispatch portion. When you're doing multiple dispatch, so here we're just specializing on the first argument. Here we specialize on both arguments, and we lose about half the speed. Performance, use destruct. This is in short. What have we learned? If you really want things fast and you can encapsulate the information in a simple enough form, use destruct, otherwise use def-class. Now, that's all we're going to say about CLOS for the course, I think. It may leak in later, but we don't have more specific topics. What I want to talk about now are just some other aspects of Lisp programming that you have to be aware of or should be aware of or should at least know about. The first one we're going to discuss is garbage collection. Now, what is garbage collection? As, well, I hear a couple of quotes by famous people pointing out that other languages don't have garbage collector, and therefore you have to do your own memory management, and that memory management is quite complicated. And when you do your own memory management, I mean, the basic problem with memory management is you freed something up and then later your code tries to access it because you didn't remember that you'd freed it. And the access then causes a problem because either the value is completely bogus or all of a sudden you're trying to access something that's outside the bounds of your program and the operating system complains. Within Lisp, Lisp has an automatic garbage collector, and that means that of all the objects that you have created, it notices the ones that are no longer being referenced by anything, and it declares them garbage and reclaims the space they're using to be used for something else. An object can be freed if no live object points to it, but unlike in some of you may have at one time programmed on computers called Lisp machines made by companies like Symbolics, and they actually ran the garbage collector all the time because they had hardware support for freeing objects with, when they freed an object, it set a bit that was provided by the hardware so that the system would know that it had to look further when it was trying to access the object. In a system on stock hardware where that particular feature is not implemented, garbage collections are done at discrete times. At the time the garbage collection is done, typically everything stops while the garbage collection is done. No Lisp code can be run. And it's at that time that the objects, many of the objects that are available to be freed, are freed. Now, there are various ways to implement garbage collection, and we in Allegro CL implement it. Here are some of the details. We first of all take the Lisp heap space, which is the area in memory or in virtual memory assigned for where we put the data associated with Lisp objects, and we divide it into two basic categories. There is an area called new space, and then a bunch of areas are the other areas called old space. Now, new space is managed with fast garbage collections that are called scavenges. New space is two identically sized halves. Only one of them is being used at any time. And so you're creating objects, and these objects are being put into that half of new space. And you're creating objects, and you're creating objects, and the system's creating objects, and so on and so forth. And all of a sudden, that half of new space fills up. When that half of new space fills up, the system then stops, and it copies. It starts looking through and finding every live object. It starts from sort of the basic pointer within Lisp and then follows it through finding every object. And when it finds an object, it says, that's a live object. And if it's in the new space half that just filled up, it gets moved over to the empty half of new space. And so all the objects from the old live half of new space are moved to the other if they are still live. And the ones that no longer are referenced are left behind. And hopefully this results in the copied half of new space having a great deal less data in it. Also, every object has associated with it a lifetime measure, which is called a generation. That is the number of times it's been moved from one half of new space to the other. And when number of generations reaches some threshold, which is initially 4, that is settable by the user, then it is moved to old space. And scavenges, which happen automatically, cannot be prevented, but are typically very fast, only clean up new space. and they leave the objects in old space alone. So an object is tenured to old space, and that's the expression, when it's moved around new space a number of times. So each time it moves from one side of new space to another, its generation is enhanced by 1. When its generation is greater than 4 in the initial condition, it is moved to old space and then becomes a tenured object. Tenured means lives in old space. Old space is not garbage collected very often. In the default, the system keeps track of the number of bytes that have been moved to old space, and when that number exceeds some threshold, then it goes and does a garbage collection of old space. That's called a global garbage collection because it does both new space and old space. In other words, it does the whole Lisp world, and that's where global comes from. It only happens occasionally, but it takes longer than scavengers, and typically nothing else can run while it's happening. Its duration may be noticeable. In the older days with slower machines, it was definitely noticeable, and your users may notice things, your interface seeming to freeze up for a second. There's a way to have, if you're using a graphical user interface, to have the cursor change to something like an hourglass. And you actually see this, if you're used to running Windows, often you're doing something in an application and the cursor changed to an hourglass, and that tells you, the user, that this is going to take a minute. You don't know exactly why it's taking a minute. You can have things change to an hourglass when there's a global garbage collection going on as an indication to users that something's going on, and therefore they won't see any changes for a minute. You can control the frequency of global garbage collection. The scavengers happen automatically out of your control, but global garbage collections can be controlled. The one thing is you almost never want to turn them off completely. The system will grow if it's deciding that new space is too small because you have too many scavengers or not enough space is freed up when you move things from one side to the other. It will cause new space to grow. Old space will grow as more and more objects are tenured, and it runs out of place to put them. Usually this happens with the allocated space of the Lisp heap growing into memory. In certain cases, you can have what looks like a trivial request for additional memory requiring a huge amount of space. Usually this can be fixed with tuning and is discussed in the garbage collection essay in the documentation. You can look at the arrangement of the heap by calling the function room. That's a standard Common Lisp function, but the output is specific to every implementation, and this is the simplest form of room, and this is roughly what it looks like in Allegro CL. We keep tweaking it. This example is from an older version, but it still basically looks the same. Here are the addresses in memory in hex and then in decimal. Here's 1/2 of new space in use. Here's the half of new space not in use. And here is one old space. After you've run for a while, you usually have a whole bunch of old spaces. But when you just start out, you typically only have one. We tell people that what you want to do is start out with the default settings of the garbage collector. And, it's always best if you don't create garbage. That's another one of those obvious statements. Interactive programs, you can arrange to trigger global garbage collections at convenient times. So when the user might be doing something that they expect to take a little bit of time, you can think to yourself, I'm going to throw in a global garbage collection here because, they're anticipating spending more time. You can trigger a garbage collection. You can trigger a scavenge with this form right here, just to call to the function GC. there are various switches. There are actually things called switches and things called parameters. And there's not much difference between a switch and a parameter. And when the system was designed, the idea was we would do something complicated, but we never did. Switches and parameters all just have single values. Switches are typically T or nil. You can turn on the print switch, and then it will print out messages when it's garbage collecting. That's all that does. And you can turn on the print switch to what's called the stats, or you can turn on stats, and that will print out information about a value associated with the garbage collection called efficiency. And every time you see a garbage collection, you get a report on the efficiency, and you generally turn these print functions on, the print and stats, if you are noticing that there's a problem. And when you notice there's a problem, you turn these on and you start looking at things. If efficiency is regularly less than 75%, then you've got a problem and you've got to figure out what's going on. You can trigger global garbage collection by calling GC with the argument P. And if you've turned on print and stats, it will tell you information about what it did. There's a global variable called global GC behavior, and it tells the system how it should trigger global garbage collections. If you set it to nil, no global garbage collections, and we don't recommend that because eventually it will cause problems. There are various additional parameters you can set as the generation spread. That's one you might want to set. That says things will live in new space for longer. Another one says make sure you do a global garbage collection before you grow the Lisp heap. This one in particular, the thing is that the ideal is Lisp is divided into objects which are created just as a sort of temporary thing, and then objects which are around for a long time, like your data. And the idea is the temporary objects will never make it out of new space, and the long-time objects will get tenured to old space. And however, the way the Lisp system runs is very complicated and opaque, and therefore you're never quite sure what's going on. And it may be that temporary objects are being sent to old space inappropriately. And you can increase the time everything spends in new space, and that might get rid of more temporary garbage or things that are quickly become garbage, or become garbage not as quickly as you want, but relatively quickly. So this is the kind of parameter change you have. Usually if you've paid for support, you ask us a question about garbage collection, and we usually have some reasonably good advice. We try to give this good advice in the documentation, but it's a complicated subject. You can specify sizes of old space and new space when you build images, and you can restructure old space and new space with a function called resize areas. And you can tenure things more or less immediately when you're loading a big application. Usually when you're loading a big application, it's got lots of data, it's got lots of functions defined, classes defined, etc. And all that information wants to get stored in old space because it's permanent information, not temporary information. So you can use a macro called tenuring, which will push things into old space more quickly than waiting for the 4 generations. A couple of specialized functions. There's something called a weak vector, which can point to objects, but that pointer doesn't constitute a reason for keeping the object alive. So when the object can be garbage collected, that is disposed of, and then the link in the weak pointer is converted to nil. You can also schedule a finalization on an object. X is value of X is some object, and function is a function. When X is garbage collected, the function will be run. There's an example of both of these in the documentation. Now, when you get a GC error, there's just one Well, there are two kinds of GC errors. One is that it says, I tried to grow the Lisp system, but the operating system wouldn't let me. When you see that, you typically call a global garbage collector, and that often solves the problem. But you also have to think about redesigning your Lisp, and you also have to think about how the Lisp application is put in the virtual memory of your machine. Sometimes it's running into things which make it impossible for it to grow, and you want to relocate it. Generally, you ask us about that, and we give you advice. But sometimes you get a GC error where the garbage collector discovers that it is confused. It has found an object which it does not recognize. And in that case, unfortunately, the only thing Lisp can do is stop, because it is in an inconsistent state at that time. And so then the question is, why did that happen? And the most cause is corrupted memory, and corrupted memory is caused by bugs in the foreign function interface. Hopefully that means bugs in your foreign functions that you have loaded into Lisp. That is, your foreign functions have accessed, typically what happens, some Lisp value, and have actually written to Lisp values and accidentally overwritten some important data. Or you have highly optimized code whose type declaration has been violated. So suppose that you have a highly optimized function which tells the system that you are going to give it a vector of 20 single float numbers, and this thing is going to fill that vector with the value, or initialize that vector with the value 1.0 in every slot. So you're going to get 20 single float 1.0s in that slot. And you actually have not, you pass it a vector which only has 10 elements. Well, if it's highly optimized code, the code doesn't do any checking to see whether the vector you gave it had 20 elements or not, because you promised it would have 20 elements, and it believed you. And so it goes and merrily overwrites the 10 elements that are actually in the vector, and then the next 10 positions in memory, and in the process of doing so, may have destroyed some data that results in the garbage collection being confused. That's what this possibility is. You recompile everything. If you think that might be the problem, you recompile everything without the optimizations and see whether the problem reoccurs. Unfortunately, garbage collection errors are not always reliably reproducible. Foreign code, I've just mentioned that. You have to worry about foreign code which accesses Lisp objects. First of all, that it's getting a valid Lisp object, and secondly, that it doesn't overwrite a value inappropriately. And there is a way to use data that's going to be allocated in foreign, used by foreign code, put in a non-garbage collected part of the Lisp application, and that will, and you can also prevent the garbage collection from running while calling foreign code by defining the foreign function with the macro def foreign call with the release heap never option. You can look that up in the manual. Now we're just going to briefly go through conditions and error handling. Occasionally you're running your Lisp application and you run into an error. And you have to realize that not all errors are bugs. They could be caused by things outside the control of your application. So you want to open a file on a file system, but the file system is not accessible. This isn't the fault of Lisp. It isn't the fault of your application. And it isn't an error in the sense that if the file system were accessible, you could do that thing. So you have to, even in a program that is without bugs, you have to be aware that certain conditions may hold that you have to write your program to deal with. Generally, when you have an application which will have users, you don't want them going into the debugger because they won't know what to do with it, and it's not useful for them. Usually, often you have an option in your application that allows an experienced person to go into the debugger, but a typical user, you don't do that. And typically, you track for errors and you provide users with options for continuation, or you just may put up a notice saying, I'm sorry, something has gone wrong, and we will now stop. And there are plenty of Windows programs that do precisely that. When you're programming, particularly when you're starting your application, you use things like eTypeCase and eCase or assert and check type, which make sure that the assumptions of your code are correct. Now, you take the eTypeCase out because you don't want errors being signaling when you're actually in your application. But when you're starting out, if you think, an eTypeCase or eCase, you think you've covered all the possibilities, and you haven't, you will get an error, and you'll know exactly where the error is. If you just use typecase and it falls through, you get a nil, and that may cause an error later, but you may not know where it appeared from. You can signal errors with the function error, cerr, which calls a continuable error, and there's also the function signal, which just signals a condition of any type, which might be errors or not. The function check type or assert is one way to test the types of arguments, or to assert various conditions hold. And these all signal errors if the checks or assertions are not true. Obviously, again, you take these out of your code when you actually have the application you give to users. You can call the function break or take a string argument, and that will stop execution of your program at a particular time, at the time you've chosen, and allows you to see what's going on at that time and see if things are going wrong. You can signal warnings, and this is something you might want to do for your users. You do this with the function warn. There are a condition hierarchy within Lisp, and different errors have different condition types. It's all represented as CLOS objects. You can define your own error classes using the macro def condition, and error handlers usually apply to specific error classes, and you can call error signaling a particular condition. There is a function within Lisp called ignore errors, and you can wrap any form in an ignore errors, and if an error happens in the execution of that form, you won't go into the debugger. Instead, ignore errors will return two values, nil and the error condition that was signaled. And so here we have safe division, and we do ignore errors, AB, and if they're perfectly good numbers, it divides them. If the second one is 0, it returns nil. Now, I have to warn you that on some systems, division by 0 produces a IEEE infinity, and that's just what the hardware reproduces, and it doesn't signal an error. So you always have to be careful to make sure that if you are assuming an error is going to be signaled, that it really is going to be signaled. Sometimes you're unpleasantly surprised in that regard. But it's always better not to depend upon an error being signaled, but if you want to know, is the denominator 0, well, test it. We have perfectly good functions for doing that. Here, you're not depending on the way the error system works. Sometimes, but one use of ignore errors, which is actually one that you are quite likely to run into, is something which is desirable, but if it can't be done, you don't care. So here we have read user init file. It's some function that finds an init file and reads it. And okay, so it couldn't find it. Couldn't find the file. Maybe the file was on a file system that wasn't loaded. Maybe the user gave the wrong name, whatever. Usually, all an init file does is it sets some parameters that to the user's liking, and usually those can be done in different ways. You just don't want the whole application typically to end because you couldn't find the init file. That's the kind of thing you can safely wrap in and ignore errors. And if you have read user init file returning a non-nil value, when it successfully reads the init file, it will return nil, will mean there was a problem, and it just, you print out some message. I had a problem reading the init file, and so I skipped it. And that will tell the user what's going on. Now, there are handlers called handler case and handler bind, and we're going to give various examples of them. I have to tell you that, again, this is an example you have to watch out for because the division by 0 may not signal an error. Actual division by 0 doesn't always signal an error because many machines support the number infinity, and when it does a division by 0, it doesn't tell you there's been any problem. It just returns an infinity. But if you do get an error signal, this thing will, the handler case will say, if there's a division by 0 error, do this, and if there's any other kind of error, do that, and if there's no error, just do what it's supposed to do. You can define your own condition. Here we've done that, and here we have we've defined a network down condition, and here we test it and signal the condition. Condition classes, all errors are subclass of conditions. You can create your own conditions, maybe subclasses of error. You can signal a condition. The signal results in the instance of the creation being created, and then the system will search for a handler, and for errors, the handler's last resort is the debugger. A serious condition, errors, a subclass of serious condition. There are a couple of other classes of that kind, and the serious condition class itself is not ignored by ignore errors, and it is typically something like the stack just overflowed, or we're out of virtual memory, or something which is going to affect the application in some general way rather than something specific like not finding a file. Here are some examples of handling errors sometimes, and I think handler bind and handler case. We're just going to go through these slides quickly because I just want you to be aware of these things exist. These are different ways of handling errors, and you can also define things called restarts, and we have some examples of using these things. They're a little bit difficult unless we were doing a whole section on errors, a whole day on errors to define these things, so I want you to be aware of them and then come back and look at these slides and also look at the examples in the documentation. Where they're in the Common Lisp ANSI standard, there are examples of everything and there are some examples within the Allegro CL documentation as well. Debugger hook is a global variable that it specifies a function to call before you enter the debugger, and it's a way in your application where you can kind of intercept the entering of the debugger, or you can provide certain GUI tools for it. So the last thing we're going to talk about, and we're just going to look through these slides, is interface development with the IDE. And so the IDE is a graphical user interface for developing user interfaces. So let's just go look at that quickly. Let's just see. We haven't looked at the list much today, so let's just look at it quickly. And so here we are. Here's what the list looks like. Now, we don't have the graphical user interface. Suppose that in our interface, this is Allegro CL 6.2. You always have a project in Allegro CL 7.0 and in 8.0, which is going to come out in a couple of months, actually like 3 months. you don't always have a current project, but you can always open one. You create a dialog that will be part of your application by creating a form which you design. It asks you, what kind of form do you want? And the one we're going to do is dialog. The other choices, if you've defined subclasses of these things, frame window, dialog, etc., it will list those subclasses as well. But we haven't done that yet. So here we have a form. That's what it looks like. And there are a whole bunch of widgets up here. And there are buttons and, you should be able to see there are buttons, there are text widgets, and there are drop-down lists, and there are tabs, and there are thises and that. So let's just take a text widget, and you click on it here, and you then go over and click somewhere on the form, and it puts it there. Now, if we double-click here, we get an inspector, and the inspector is telling us various aspects of this little widget or control. It's saying available. That means can the user type to it? A user should be able to type to it. Let's run the form. There's a menu here called Run. It says Run Form, and then it asks you if you want to save things, and we don't. And so here's an editable text widget, and hey, I can change it. I can edit it. And if we had actual program, let me just do one more thing, and then we'll go back to, there's an option on the Tools menu called Get Component. When you click on it and then you click on something, it returns that object. And so set QRR star. Now the value of RR is our editable text widget. And what is its value? Oops, if I could learn to type here. LUE of RR. And the value of RR is new text. That's exactly what it says. And if I change it again, new words. And come down here and look at the value again. There we go, new words. So you stop testing a form by hitting the button there. Slightly more complicated if you run a project because you can't use Get Component, but there are other ways to access things. So anyway, there we are. We put an editable text widget on there, and we can put other widgets. Here's a button, and here's a multiple value list where you can choose more than one thing, and so on and so forth. So that's what designing with the IDE looks like, and you create windows, dialog boxes, menu bars, et cetera, and use the text editor to write your code, and it produces skeleton code for you that is suitable. And what's going on? I hit that. There's a package called the CG package or Common Graphics package where there are a whole bunch of functions with interacting with Windows, drawing graphics, etc. It says it's available only on Windows, but we do have a test version on Linux. A project is a thing that collects all files associated with an application and manages them. And there's something called the project manager, and it lists the files and various windows and other things associated with your project. A form is what we just saw. You get a form with the new form choice of the file menu, and then you're asked what kind of window do you want, and you choose. And generally, when you're programming an application, you subclass the predefined classes so that when you write methods, they affect your windows only, rather than affecting other things that are defined in the Common Lisp system. When you double-click on a form or an object within a form, you see the inspector inspecting the that object, and you can typically you change certain of the fields. There's the class, which is the type of dialog it is. There's the name. There's the title. Then there are menus, scroll bars, background and foreground colors, etc., etc. Let's just quickly go to the application, and let me just show you that. So here's the, let's edit the form. So there we're looking at the form, and let's do background color. Where is it? Here we go. Background color is nil, meaning use the default, but we're going to pick one. And you say, I clicked on that little thing there, and I got a color choice thing, and let's pick, one of these nice, hideous things. And hey, there we go. There's the new background color. And notice it didn't change the background color for these things because they're themselves. Let's do that just for our editable text widget, this lovely turquoise. And there we go. So here are some examples. And again, I'm not going to go through these in any detail because they're a little bit complicated, but they're here for you to look at. There's also a tutorial within Allegro Common Lisp. The tutorial runs you through a more complicated example, shows you many things to do. I'm going to show you another way to find examples shortly. But the thing you always start out is you start out with your own class. So we have a paint buffer with, and that's a subclass of frame with single child. The general window with a title bar and a frame and a border is a frame with single child. Its single child is called the pane, and that's where the data goes. So you always define a subclass of frame with single child, and then a subclass of bitmap pane, and then you associate the two with the default pane class method applied to your paint buffer is the paint pane. Messages, the operating system uses something called send message, and it happens with key press or Windows need display or whatever. Common Graphics translates these into generic functions. Redisplay window is one of these generic functions, and you can define your own redisplay window method that will draw things appropriately if that's what you want to do. There are various event handler functions with names like redisplay window, which is we've already looked at, resize window, mouse left down, virtual key down, user close, etc. Those are describing Windows events, and you can write your own code that will specialize on your own objects. Here's a sample of the user close method where it asks you, do you really want to do this? Do you want to save the files that you've created? Typical dialog boxes, there are a whole bunch predefined in Windows, and you have various functions like pop-up message dialog, ask user for new path name, ask user for existing path name. These just bring up standard Windows dialogs. There's a function, or a generic function actually called invalidate, which calls redisplay window. And typically, you call invalidate. You've defined redisplay window methods, but you call invalidate in order to trigger them. You don't typically call redisplay window directly. You want the system to do that because it will call it with the right arguments, which are system dependent, and you actually don't know what they are typically. A whole bunch of standard widgets. I showed you some. Drag and drop GUI builder. I put the editable text on. I put a button on, and you can move things and you can align them. We'll just do a couple of those things in a minute. I just want to, not too many slides left, but for the most part, the properties like size and position can only be set during the design stage. But the things that actually are showing what's going on are properties like the range and the value. You notice the value changed, and you can set the value programmatically. You can access the value after the user has changed it. There's a function called find component, which finds objects and by name, and therefore it's a way for you to get a handle on objects. The thing I showed you was using the get component menu choice. Of course, you don't normally have that available. Instead, you know the names of the objects and you use find component to get a handle on the objects. There are a whole bunch of event tabs, and those you write event functions with names like onClick, onChange, onMouseIn, etc. You can associate your functions with those, and those functions will be run when you click over an object, when an object changes its value, when the mouse moves over it, etc., etc. The general naming convention of events of the functions you write are form name, gadget name, event name. So it would be form1 my editable text widget on click, something like that. You'll see these in the editor if you use these things. Just want to mention to you there's a powerful widget which is defined within Lisp called the grid widget, which is basically a spreadsheet. And you can see examples of that by looking, we'll do this in a second, looking at the examples list. When you're using the grid widget and when you're using many of the predefined widgets, you want to make appropriate subclasses. And we've discussed how to do that here. Grid widgets have rows and columns. I'm just putting up some slides about the grid widget because it's a fairly interesting thing. Grid widgets will display data with generic functions like read cell value, gets the data, draw cell, displays it, and you customize those things to your purposes. Here are just some more grid widget things, cell click and write cell value. It's just I put these slides in so that if you try out the grid widget, you'll have some idea of what the various things you're working with are. There are these grid widgets examples provided, a simple color editor, a replicated editable text columns, and then a much more complicated example where you sort of are running the database for a human resources department. There's another application defined in Allegro CL called Allegro Serve. The web application server allows you to create and publish web pages, and it generates HTML, and you can create pages dynamically, and you can modify them dynamically. A static page has contents which changes rarely, like your head page of your web thing. A dynamic page is generated in real time based on current information. So a shopping cart of a store website is a typical dynamic page. We have a particular addition to that called Web Actions, which adds more dynamic capabilities. And all of this available for 7.0, also available for 6.2. Here's where the documentation, you just go to the main documentation page, which is called Introduction, search for AServe and Web Actions, and you can look at the documentation. Now, before we quit, we're just about done, and we actually got through all the slides. I just want to go back and show you a couple more things with the, here's the button. What do you do with a button? You press it. And then we're now investigating the button here, and so I want the on-click to be, I want it to change. So here, the editor comes up and says Form 2, Button 4, on-click, dialog, widget, and let's just try this. Blue is a predefined color. Let's save that. Yeah, sure, why not? And now let's run the form. Here's the form. Let's run the form. I don't know if this is going to work, but it's the kind of thing you do. And sure, why not? And sure, why not? And yeah, after you save lots of files, why not? And then you click on button, and well, the background color of the button is hard to see, but it is back there. Here, let's have a look at this one. Let's get that object there, and where are we? We want the debug window. So there we are, multi-item list, set Q, MM to that. And so let's just look at two things. Range of MM, whoops, is 1, 2, 3, so set F, range of MM to 1, 2, 3, 4. Oh, yeah. So what did I do? I forgot to put a quote right here. And therefore try to evaluate the list. And so let's go back, and there we go, 1, 2, 3, 4. And we can dynamically change, let's look at value of MM should be a list of 1 and 2, and we do set F. This time we'll do it right. 4. And there we go. And if we change it here, we can, you have to press Control to pick 2 things. And then we come back here, and the value's changed again. And so here we stop running the form. Those are just some of the techniques you can use to design your application. Oh, let me just, it's toggle save, but let me just show you one more thing really quickly. I just want to show you when you're designing things, let's see, we stopped running on that form here. Yeah. When you're designing things, you can move them around. And you notice when they're aligned, let's see, do you see that? You may not see that. Yeah, you see a little bit slow there, but you see lines are appearing. Those are telling you when you're aligned with the other widget. I can move this around. It will eventually move. You see that little line there saying, okay, the new position is aligned with the other widget. So there are various little helpful design tools like that. Okay, that's the end of the course. I want to thank you all very much for participating. Happy to continue answering questions on either the homework or anything that we've covered. Again, the homework is at this particular website, www.electronics.com. That should be a slash. Ignore the dot. That should be a slash there. So just pretend it is. And also send mail to training@franz.com if you want. It's been a pleasure, and I hope you've all enjoyed the course. We're just going to have a few minutes, a few seconds of silence so that the recorder knows to stop.